Hello everyone, my name is Matt Halm.
And I'm Sam Pfrommer.
We are presenting our method, ContactNets, for learning discontinuous contact dynamics. Success in classical robotics methods has often been enabled by careful consideration of the mechanics of frictional contact. While physics-based structure is often absent from purely data-driven methods, they must still be effective at capturing and controlling frictional contact because it is the fundamental process that drives robot motion. Unfortunately, contact, and particularly discontinuities due to impact and stiction, have empirically been a pain point for deep learning methods. This can be seen, for example, in video prediction, where contact induces distortions or high uncertainty. Theory suggests that deep learning is fundamentally biased towards smoothness in direct conflict with discontinuity. Furthermore, extreme stiffness in the motion can cause numerical issues in the training process itself. Our parallel work and submission to ICRA offers a quantitative study into these effects. In this work, we rectify these issues in a common robot learning task, fitting a dynamics model to state transition data. Our method, ContactNets, learns contact dynamics in a well-conditioned manner by capturing discontinuity with a smooth, implicit representation. It is additionally flexible enough to capture a wide variety of robotic systems and does not require any tactile sensing data. ContactNets takes inspiration from this visualization of a bouncing ball. Despite the fact that no ground is drawn, humans can intuitively notice that the locations of each of the impacts and smoothly interpolate between them to hypothesize that the ground is flat. As an analog to this process, we implicitly learn contact behavior as a sign distance function phi and a friction Jacobian JT. Here, we show how phi and JT control the behavior of contact in physics-based dynamics, including those which underpin robot simulators like MuJoCo, Drake, and Bullet. Terms related to contact-free motion, shown in yellow, are often simple expressions such as gravitational acceleration or are easily identifiable in the case of many robotic platforms. Model class complexity is instead driven by phi and JT, which can represent arbitrary object geometries with spatially varying and anisotropic friction. ContactNets performs prediction with an identical structure, except that phi and JT are replaced with functions learned from data, such as a deep network. While these functions are often smooth, discontinuity is generated implicitly in a contact force solver via numerical optimization. The drawback of a discontinuous model f theta is that naive prediction loss is ill-posed, as the loss itself becomes discontinuous in the parameters. We rectify this issue with a novel mechanics-based loss, which optimizes over a set of hypothesized contact forces lambda and penalizes two terms. The prediction term L1 penalizes difference with the observed net force, which can be constructed from the state transition directly without tactile sensor data. The physics term L2 instead encourages the contact forces to comply with the physical constraints of the simulator's contact force solver. Evaluating the loss itself becomes a tractable quadratic program, transforming the training process into a bi-level optimization problem.
To evaluate our method, we use April tag tracking to collect pose data for over 500 tosses of a cube onto a flat surface. The baseline approach, shown here, is straightforward end-to-end learning with a neural network, where contact force is learned directly from observed state transitions. While the network somewhat captures ground impact, its continuous nature prevents it from avoiding penetration or coming completely to rest. By instead using a standard physics simulator and supplying our learned sign distance function and friction Jacobian, we are able to capture discontinuous impact as well as stiction. The simulated trajectories come fully to rest with minimal penetration, satisfying fundamental properties of contact dynamics. As shown in the figures on the left, this gives us significantly improved positional accuracy and far better rotational accuracy compared to the baseline end-to-end method. Our methods are also an order of magnitude more data efficient, needing just over 30 training tosses to exceed the baseline's performance on all 256 training tosses. We've demonstrated that our parameterization fundamentally captures complex contact behavior in real-world situations. Future work will involve multi-object manipulation experiments and extensions to our model. Thank you to our supporters at Google and the National Science Foundation for making this work possible.